Few-shot and meta-learning address one of the most persistent constraints in modern artificial intelligence systems, the limitation of labeled data. In real-world AI teams, especially in healthcare, robotics, industrial inspection, and enterprise analytics, acquiring large annotated datasets is expensive, slow, and often restricted by compliance requirements. Systems must adapt quickly using minimal supervision while maintaining reliability under distribution shift. Few-shot learning formalizes learning from small support sets evaluated through query sets within episode-based training. Meta-learning extends this by optimizing models to adapt efficiently across task distributions rather than a single static dataset. In production environments, this distinction shapes system design, experimentation frameworks, and even hiring decisions. Teams building adaptive AI capabilities prioritize engineers who understand task sampling, generalization behavior, and learning curve dynamics over those focused solely on scaling infrastructure. Most early AI professionals misunderstand this domain by assuming performance bottlenecks can always be resolved by collecting more data. In many industries, that strategy is neither feasible nor strategically sound. Professionals who master data efficient learning frameworks move beyond implementation roles and into architecture and research aligned positions where adaptability and long term robustness define impact. This lesson develops a rigorous understanding of how AI systems operate when supervision is constrained. Few-shot learning introduces structured N-way K-shot tasks built around support and query sets using episode-based training. Meta-learning reframes optimization by training models across task distributions rather than a single dataset. Transfer learning provides mechanisms for reusing representations efficiently across domains. In real-world AI teams, these competencies appear in personalization engines, adaptive robotic systems, cross-domain computer vision, and low-resource natural language applications. Engineers are not evaluated solely on accuracy metrics, but on how effectively systems adapt to new conditions with minimal data. This distinction frequently influences promotion decisions and role specialization within AI organizations. A common career mistake is remaining too focused without internalizing adaptation dynamics. Professionals who fail to understand task level reasoning often plateau in mid level implementation roles. Mastery of these objectives strengthens architectural thinking and builds credibility in both research oriented and production driven AI environments. Limited labeled data introduces statistical fragility into deep learning systems. When data sets are small, neural networks tend to memorize patterns rather than generalize, resulting in overfitting and unstable performance during deployment. In production environments such as medical imaging or industrial quality control, collecting thousands of high quality annotations is often unrealistic due to financial and regulatory constraints. AI teams must balance model iteration speed with annotation budgets. Engineers trained exclusively on benchmark scale datasets frequently struggle when transitioning into low resource industrial contexts. Distribution shift further amplifies this risk because small datasets rarely capture the full variability encountered in production. Most early practitioners assume infrastructure scaling will compensate for data scarcity. In practice, architectural strategy and data-efficient training approaches determine long-term reliability. Professionals who understand this constraint design validation protocols that simulate task diversity, reducing deployment failures and demonstrating the system's level maturity expected in senior AI roles. Few-shot learning is typically structured as N-way K-shot classification, where each episode samples a task from a broader distribution. A small support set defines class representations, and performance is evaluated on a separate query set. Episode-based training aligns optimization with real deployment scenarios rather than static dataset performance. In production AI teams, this paradigm mirrors situations where new categories or product types emerge with minimal labeled examples. Engineers must design task sampling strategies that realistically represent operational diversity. Poor task design leads to misleading evaluation metrics and fragile systems. A common professional misconception is treating few-shot training as conventional supervised learning with smaller batches. The conceptual shift lies in optimizing adaptability across tasks rather than maximizing accuracy within one dataset. Engineers who internalize this paradigm gain credibility in adaptive system design and research integrated production environments. Metric learning approaches frame few-shot classification as a problem of representation geometry rather than heavy parameter adaptation. Models such as prototypical networks compute class centroids in embedding space, while matching networks and Siamese architectures compare pairwise similarities using learned distance functions. The objective is to learn a metric space where semantically similar inputs cluster together with minimal supervision. In real-world AI teams, metric learning is frequently used in visual search, product categorization, and anomaly detection systems where new classes must be introduced without retraining the entire model. Engineers who understand embedding stability and distance calibration are often more effective than those who rely purely on scaling deeper architectures. Most early professionals underestimate the importance of representation geometry. They assume larger networks automatically produce better few-shot performance. Model-based meta-learning embeds adaptation mechanisms directly into network architecture. Recurrent structures such as LSTM-based meta-learners and memory-augmented models learn to update internal representations when exposed to new tasks. Neural Turing machines extend this idea by incorporating differentiable memory components that enable structured reasoning across episodes. In research-oriented AI teams, these architectures are explored when rapid adaptation is critical and task distributions are highly diverse. However, production deployment introduces operational challenges, including interpretability, debugging complexity, and computational overhead. A common career mistake is prioritizing architectural novelty over production stability. Early professionals are often attracted to complex models without evaluating maintainability or infrastructure cost. Senior engineers assess whether architectural flexibility justifies operational risk. Optimization-based meta-learning explicitly trains model parameters to adapt quickly with minimal gradient updates. In model-agnostic meta-learning, an inner loop performs task-specific updates, while an outer loop optimizes the initial parameter configuration across tasks. The goal is to learn an initialization that generalizes efficiently to unseen problems. In production AI systems, this framework is applied in robotics control, personalized recommendation systems, and adaptive forecasting pipelines. Engineers must understand nested gradient flows and computational trade-offs to implement these methods effectively. A common misunderstanding is equating MAML with simple fine-tuning. The distinction lies in meta-optimizing across task distributions rather than adjusting after training. Professionals who grasp this nuance make stronger architectural decisions and avoid overestimating the practicality of complex meta-optimization pipelines in resource-constrained environments. Learning to learn formalizes how prior experience across tasks influences adaptation speed and generalization performance. Inductive biases learned during meta-training determine how quickly models converge on new tasks. Theoretical analysis often focuses on bias variance trade-offs across task distributions rather than within a single dataset. In real-world AI teams, learning curves are often more informative than final accuracy. Organizations measure how performance scales as limited data becomes available, especially in personalization and low-resource domains. Engineers who analyze adaptation efficiency contribute strategically to roadmap planning and infrastructure allocation. Most early AI professionals ignore task-level bias considerations and focus narrowly on benchmark metrics. This behavior limits long-term growth. Professionals who internalize theoretical foundations while grounding them in deployment constraints are more likely to transition into research leadership or principal engineering roles within adaptive AI teams. Meta-learning assumes tasks are sampled from an underlying distribution. Generalization performance depends heavily on how representative the meta-training tasks are of future deployment conditions. If task sampling lacks diversity, the model may overfit to a narrow subset of problems and fail during meta-testing. In real-world AI teams, this translates into careful construction of task splits that reflect operational variability. Cross-domain few-shot evaluation is increasingly used to assess robustness. especially in enterprise systems where data distributions evolve over time. Engineers responsible for experimentation design must think beyond random splits and consider structured task diversity. A common career mistake is underestimating the importance of task distribution design. Many practitioners focus exclusively on architecture while neglecting evaluation rigor. Transfer learning leverages pre trained representations to accelerate learning in new domains. Domain adaptation adjusts models when training and deployment data distributions differ. In few short contexts, cross domain transfer becomes particularly important because labeled examples are scarce. In production environments, transfer learning is often the first strategy before implementing full meta learning systems. Engineers must evaluate similarity between source and target domains, monitor for negative transfer, and design controlled fine tuning experiments. A frequent misunderstanding among early practitioners is assuming pre trained models generalize universally. In practice, domain mismatch can degrade performance significantly. Professionals who rigorously evaluate transfer assumptions reduce deployment failures and build a reputation for disciplined experimentation rather than optimistic overconfidence. Zero shot learning enables models to make predictions for unseen classes by leveraging semantic information such as textual descriptions or attribute vectors. Instead of relying on labeled examples, the system maps inputs into a shared semantic space aligned with external knowledge representations. In industry AI systems, especially multimodal applications, zero shot capability reduces annotation requirements and supports rapid feature expansion. However, the quality of semantic alignment directly determines reliability. Most early professionals assume zero shot learning eliminates the need for data. In practice, supervision is shifted upstream into representation learning and semantic modeling. Engineers who understand this nuance avoid unrealistic expectations and design more grounded, interpretable, cross modal systems suitable for production deployment. Multitask learning trains a model on multiple related objectives simultaneously, encouraging shared representations that improve generalization. It acts as a form of inductive bias by constraining parameter updates across tasks. In real world AI teams, multitask frameworks reduce redundancy across pipelines and improve parameter efficiency. However, conflicting gradients between tasks can introduce optimization instability and degrade individual performance. A common misconception is assuming that adding more tasks automatically improves results. Without careful loss, balancing, and monitoring of gradient interference, multitask systems can underperform. Professionals who understand these trade offs demonstrate architectural maturity and are better prepared to manage complex AI product ecosystems. Continual learning addresses scenarios where models encounter tasks sequentially rather than simultaneously. Catastrophic forgetting occurs when learning new information overwrites previously acquired knowledge. This presents a significant challenge for adaptive AI systems deployed in evolving environments. In production systems such as recommendation engines or monitoring platforms, continual adaptation is essential. Engineers must balance stability, preserving prior knowledge, with plasticity, incorporating new information efficiently. Many early practitioners retrain models from scratch when data changes, increasing infrastructure cost and operational downtime. Professionals who implement structured continual learning strategies reduce retraining frequency and extend model lifecycle, positioning themselves as long-term system owners rather than short-term experimenters. Data augmentation expands limited datasets through controlled transformations or synthetic generation. In few-shot learning, augmentation supports representation robustness by increasing variation without requiring additional labeled examples. In real-world AI teams, domain-specific augmentations and contrastive learning pipelines are frequently used to improve embedding stability. However, unrealistic transformations can introduce bias and degrade generalization. A common professional mistake is aggressive augmentation without validation against deployment distributions. Engineers who align augmentation strategies with operational data characteristics produce more reliable models and demonstrate disciplined experimentation, a key differentiator for senior AI roles. The next session extends data efficient learning into uncertainty modeling and Bayesian deep learning. While few shot and meta learning focus on adaptation speed, uncertainty quantification addresses confidence and risk awareness in predictions. In production AI environments, understanding epistemic and aleatoric uncertainty influences deployment thresholds, human in the loop systems, and regulatory compliance. Engineers must evaluate not only what a model predicts, but how confident it is under distribution shift. Many early professionals optimize for accuracy while ignoring confidence calibration. This behavior leads to overconfident failures in real deployments. Professionals who integrate uncertainty reasoning into adaptive systems move closer to research level maturity and are better positioned for high responsibility roles within AI organizations. If this session helped you think deeper about how AI really works in production and in careers, then you're exactly the kind of learner this channel is built for. At Life Decode, we go beyond surface level tutorials. We break down complex ideas in artificial intelligence, finance, and real world career growth into structured, practical understanding. If you're serious about building long term capability, not just collecting tools, subscribe to Life Decode, and I'll see you in the next lesson.